Non-ideal solutions. In previous lectures, we have discussed about the ideal solutions which obey the Raoult's law. So there are certain pairs of miscible liquids which obey the Raoult's law. Throughout the complete range of the concentration at given temperature, these pairs are as follows. So first one is benzene and bromobenzene. The second is benzene and ethylene dichloride. And the third one is ethylene dibromide and propylene dibromide. So these are the examples of the real mixtures which obey the Raoult's law and behave ideally. However, there are many systems of pairs of liquids which do not obey the Raoult's law. To a greater or lesser extent, it depends on the nature of the liquids and the temperature. So in order to understand the deviations of the solution from Raoult's law, it means that the solutions are behaving non-ideally. Let's understand the graphs between the mole fractions and the vapor pressures. So we observe that there are three types of solutions which show non-ideal behaviors and they show deviations from the Raoult's law. For the type 1, those pair of liquids whose total vapor pressure are intermediate between those of pure constituents. So first example is if we plot a graph between compositions and vapor pressures for cyclohexane and carbon tetrachloride system, then we observe that the graphs pass above the expected straight line of Raoult's law. Anyhow, the total vapor pressure is all the times intermediate between the vapor pressures of two components. The following diagram make the idea clear. So let's see the diagram. So here we have a diagram with liquid A with mole fraction XA and liquid B with mole fractions of XB here. So this diagram is similar which I have explained in the previous lecture, which was following the Raoult's law with this straight line. So for the non-ideal solution, the expected straight line is deviated to an actual graph that is in a curved form. So for this type 1, there are some examples like we have methanol and water, benzene and toluene, benzene and carbon tetrachloride, cyclohexane and carbon tetrachloride. Such pairs of liquids create the forces of repulsion to some extent as compared to pure components. This makes the vapor pressure greater than the expectation. So here we can see that the deviation from the straight line is positive. It means the total pressure of the system is higher as compared to the expected line or the expected ratios for at different solution concentrations with respect to the different vapor pressure, that is the total vapor pressure of the system at variable concentrations. So for example, for this line, if the vapor pressure of the system is at this point for the ideal solution, but it's higher for the actual non-ideal solution. So this higher vapor pressure means that the interaction between the particles present in the solution are less than the proposed ideal behavior. So this positive deviation is due to the repulsion between the two types of liquids which are miscible. The second type of non-ideal solution is like the previous one, but it have a maximum point in the total vapor pressure curve. So this point is describing to a specific mole fraction of the component A and B at which the interaction is minimum. So here we have a few examples like benzene and cyclohexane, benzene, ethanol and chloroform, ethanol, water, propyl alcohol and water. The structure of propyl alcohol is given here, and dimethyl ether and carbon disulfide. For these kinds of mixtures, the expected straight line that must, or better to say, supposed to follow the Raoult's law, but actually the experimental graph is showing a positive deviation but with a maximum point in the total vapor pressure curve. The third type of non-ideal solutions are the certain pairs of liquids that show a minimum point in the total vapor pressure curve. They show the forces of attraction among the molecule of the pure component. It means that if the solution or the mixture have lower total pressure, that is the experimental, as compared to the expected line, showing the more interaction between the different particles. So this higher interaction or intermolecular forces make them to stay in the liquid form or in a connected form, resulting the low concentration or the low contribution of the particles or molecules which are free from the intermolecular forces and they are occupying the surface of the liquid, which contribute to the vapor pressure of the solution or mixture. Here we have some examples which are showing the negative deviation. It means that the interaction between the two liquids is stronger as compared to the interaction between the one liquid and the other liquid. Like for example, if we have water and HCl mixture, the interaction between water and HCl is stronger as compared to the interaction between the water or HCl molecules.